Hello everyone, welcome back to the lab section of CE 3300. Today we'll conduct a lab test to determine the overall performance associated with a pump. In hydraulic engineering, we are primarily interested in pumps for irrigation, flood control, water supply, and many other uses. A pump is a device that moves fluid by mechanical action. It typically converts the electrical energy into hydraulic energy, and this energy is added to the flow of water. There are two types of pump: the axial flow pump and the radial flow pumps. In axial flow pump, the flow is axial to pump shaft, and in radial, the direction of flow is radial to the pump shaft. One of our objectives in this experiment is to produce the performance curve, and this can be done by the following relationships: head coefficient versus discharge coefficient, power coefficient versus discharge coefficient, and efficiency versus discharge coefficient. The formula for head coefficient is given by del H divided by n square t square by g, or del Hg by n square t square. So where del H is the head increased by the pump and n square is the square of rotational speed of the impeller, d is the diameter of the pump impeller, and g is the acceleration due to gravity. Power coefficient is given by the formula P divided by rho n cube d to the power 5, where P is the power supplied to the pump, rho is the density of water, n is the speed of the rotation of impeller, and d is the diameter of the pump impeller. Discharge coefficient is given by the formula Q divided by n d cube. Q is the water discharge, n is the rotational speed of the impeller, and d is the diameter of the pump impeller. And the efficiency of pump is determined by the ratio of P over the electric power to the pump, PE, where P is the power added to the flow system, which is given by the formula gamma Q multiplied with del H. And to calculate del H, we'll use the conservation of energy formula, which is shown here. The pump used in this experiment is a Berkeley pump. It is an axial flow pump. The impeller diameter is 7.94 inches, and the pipe diameter at which the pump discharges is 6 inches. Other instruments used in this experiment are the tachometer, which measures the rotation speed, pressure gauge, which displays the pressure inside the pump, a measuring rod, and the flow tape, which shows the depth of the water, and control valve, which controls the discharge in the pump. To calculate the discharge rate, we'll use the weighing bucket, which you have used in our last experiments. This is the pump, and the reservoir of water is underneath the pump. First, we need to measure the depth of the level of water from the center line of the pipe. For this, we use a long rod and dip it into the reservoir. Remember, our reference point is the center line of the discharge pipe. Then we'll measure the depth using measuring tape and the rod. After the depth is measured, pump 2 is turned on. After the motor is turned on, water is drawn from the reservoir into the discharge pipe. Here the flow is controlled by this valve, and it goes into the channel. The flow of water continues through the channel and ultimately ends in the weighing bucket. The control of flow to the bucket is done by the gate, and we also need to close the exit valve of the bucket to calculate the discharge rate. The weight of the bucket is noted from the display monitor. The control valve controls the discharge, and this control valve has 7 control points starting from 0 to 6. We have started our experiment from the position of maximum discharge. After taking the readings for the volumetric discharge rate, we'll take the reading for pressure from the gauge. Then we'll take the reading for delta Z, which is measured with the help of the floating rod and the measuring tape. The next step is to measure the rotating speed of the shaft. For this, we'll use the laser tachometer. The laser is put on the shaft, which has a reflecting strip. The tachometer displays the speed of the rotating shaft in RPM. The electrical power to the pump is noted from the display menu of the pump controller. After taking the readings for the discharge rate, del Z, pressure and input power, we'll change the position of the control valve and repeat the entire procedure. Here I have changed the control valve to a new position, and you can see the changes in pressure reading, del Z and input power. After the experiment is completed, the observation table will look something like this. In your report, you need to include the following things: the experimental setup and how you obtained the measurements in the observation. In theory, you need to describe how the energy equations are used and dimensional analysis is used to determine the four dimensionless coefficients. In the results, we need to plot the CH versus CQ, CP versus CQ, and eta versus CQ, and discuss the curves in terms of the expected curves typical for axial flow pumps, the efficiency obtained with the pump, and the optimal value of head and discharge associated with the pump. Also, please discuss if the head loss is included, how will this affect the results, and how can we determine the head loss based on what we have learnt in the course so far. Please strictly follow this format in your lab report, and your lab report is due on April 26th, 5 p.m. That is a Monday. And if you have any doubts, please feel free to email me and we can schedule a Zoom meeting if needed.